Hello and welcome again to Functional Programming course. My name is Dmitry Soshnikov, and this time we will talk about one more interesting idea called numerical data structures. As you probably know, there is something called natural numerical system, when we represent number n by n symbols in a certain alphabet. So we need an alphabet which consists of only one proper symbol, which can be represented as this vertical dash or 1 or something else, and one improper symbol which separates numbers from each other. And number 5, for example, we can represent using 5 vertical dashes. How can we do that in F sharp? In F sharp, we can say that this natural number would be either 0, which would correspond to number 0, or we can define the constructor suc from successive element of any other natural number. So this number 5 would be defined as suc of suc of suc and 5 times of 0. And this is definitely not the most efficient way to represent numbers. The good thing is that adding those numbers together looks very natural. We just kind of glue those two things together. But to implement that in F sharp, we need to implement something very similar to appending of two lists. So we can say that, okay, if you want to add number x to 0, then we just return x. If you want to add number to the successive element of z, we need to add z and x and then take the successive element of that. That is natural, but the complexity of this addition you can probably understand is big O of n. And implementing addition with the complexity of big O of n is something not right. However, you can see that there is a direct analogy to normal lists. So normal list is a collection of elements. We just distinguish between different elements. With the numerical system, we say that elements are of the same kind. They are always just vertical dots. But with lists, we also store the current element of the list. In this case, we don't store anything. We just take the successive element. And you can see that addition is very similar to append in the nature. And in fact, what we can do, we can say that adding 1 is the same as list constructor, constructing some arbitrary element to the list. Minus 1 corresponds to tail of the list, addition corresponds to append, and 0 corresponds to empty list. In fact, that gives us the idea that we can use lists to represent numbers. So for example, we can say that type net is just list of characters. In this case, add would be append, suc would be some kind of cons of some character, let's say 4, and previous element would be tail. So that here we see that this natural numerical system is similar to lists. But there are other numerical systems which we use. For example, in our everyday life, we don't use a natural numerical system. We use a numerical system with the base 10, right? We use decimal system. So why do we use decimal system? Because in natural numerical system, numbers are too long. We don't want to write how much money we spent in the supermarket by this huge number of vertical lines. We want just to say things like 54, 42, and have those short notation correspond to longer numbers in natural numerical system. So the same idea can lead to the fact that numerical system corresponds to lists. We can probably think of some more efficient ways to implement lists, which are similar to using numerical system with higher base. So for example, in decimal system, we can add numbers faster because the complexity of addition, if we add them, digit by digit, corresponds to number of digits, and number of digits is logarithmic. In this sense, we can think of like which numerical system is optimal, and optimal, it's not always clear what do we mean by optimal, but sometimes we say that we can try to think of the density, how much information the digit holds. So for example, if we have the base k, n digits, can give us k to the power of n minus 1. This is the largest number that we can represent. But having a lot of digits also adds complexity, because we need to consider all them as a special cases. So if we think of like the system which would correspond to highest expressive power of each individual digits, we need to take this function and look for its minimum. And if we do that, we can see that the optimal numerical system would be the one with base e, because when we have e as the base of the system, we have this minimum of this function. However, it's not really clear like how can we have the base which is non-integer, but it hints that probably the optimal systems are the ones which are around e, which means either 2 or 3. And that is one of the reasons that why binary system is turns out to be quite useful, and also why there were some actually attempts to create um, the the, the computers which are based on the system with base 3. So the main idea is that once we switch to either binary or any other base, we start having numbers which are much more expressive, and the length of a number is logarithm from the number itself. So even though it's a binary logarithm, it's still much shorter than the original number in the natural numerical system. So how can we turn this idea and implement it into lists? In fact, what we can do, we can come up with something called binary lists. And binary lists is a list which is built according to the binary system. So let's see how it can be defined in F#. So again, the binary list can be either an empty list, and then it can be 0. So it can be the B list of pairs of type A. So you see, the interesting thing is that in each element of the list, instead of storing one thing, we would store a pair. So for example, if we want to store the list 1, 2, we just have the list of length essentially 1 with the pair of elements. But sometimes we need to store the 3 elements, for example. In this case, when the number of elements is not even, we need to add an extra element. So it would be 1. And if the constructor is 1, we would have an element and then remaining B list of pairs. So let's see how it works out for normal list like 1, 2, 3, 4, 5, 6, 7. So empty list is represented by nil. If I want to store just one element 1, I use the constructor 1 and the empty tail. Now, if I want to store 1, 2, as I mentioned, 1, 2 is the list is one element. It's stored as a pair. So what I would store here, I would store 1, because it's an element of one list, the list of one element. This one element is a pair of 1, 2, and then this constructor is 0. Now, if I want to add one more element and store 1, 2, 3, how would I do that? I would need to store it as 1 again. 1 would be stored as 1 as an element, and then I would have the remaining list of pairs to 3. Now again, 1, 2, 3, 4, it becomes 0, 0, and then 1 and list of pairs. So this would be an interesting thing here. It would be a pair of pairs, and it would be the B list of pairs of pairs. So you see, this implementation allows us to represent list in more compact way. So we pack many elements into the same type, which allow us to have actual data structure become smaller at the cost of more tricky processing. Because if we want to process, if we want to traverse this element, we would need to kind of unpack it from pairs back to the original list. So unfortunately, the power of type structure of F# doesn't allow us to implement efficiently the operations of this data structure, so we will not go into details and we will not implement this. But the main idea, I think, is pretty important to be mentioned, that sometimes we can have those interesting types which are inspired by the way we write numbers using numerical systems in our everyday life.